Okay. These are three results. We were discussing if 8.82 and 8.3 yesterday, that if there is any eigenvalue 0, then A is a singular, has no inverse. Determinant is 0. A singular, has no inverse. Determinant is 0. And the second result is that if A is a non-singular, mean no eigenvalue is 0, then the eigenvalues of A inverse are simply reciprocal of eigenvalues of A. If lambda is an eigenvalue of A, then 1 over lambda is eigenvalue of A inverse, but the eigenvectors remain same. Now, the last result is if we have upper triangular matrix like A, lower triangular matrix like B, or a diagonal matrix like C, then eigenvalues of these matrices are simply their diagonal elements. Yani these elements. These are the eigenvalues. After this, we have just exercise. First few questions are to verify given vectors are eigenvectors. That's simple, multiply them. So you will have A multiply K and will get equal to lambda time K. Then question 7 up to 22 are to find eigenvalues and corresponding eigenvectors. Use theorem 8.8.2. Or state whether the matrix is a singular or non-singular. And if you get an eigenvalue of a matrix which is equal to 0, then you can say it is a singular. And question number 23, 24, 25, 26. These four questions are where you need to find eigenvalues of A inverse. But first you find eigenvalues and eigenvectors of A. Then you write eigenvalues and eigenvectors of A inverse. So here we have done everything we need to do in this exercise, all questions. And the next section we have in our syllabus is 8.10, which is orthogonal matrices. This is section 8.8, and next section in our syllabus is section 8.10. Now here, since I have shown you this eigenvalues and eigenvector for a complex 2 by 2, for a real matrix, examples are given. So you can do more questions, as many as you want, to learn this material more. Section 8.10. Section 8.10 is orthogonal matrices. orthogonal matrices. So what is this definition of orthogonal matrix? A matrix is orthogonal if it is equal to its transpose. If A is equal to A transpose, then it is defined as an orthogonal matrix. No, it is first it is symmetric. A transpose is equal to A inverse, then that is orthogonal. So first of all, the definition is an n by n matrix A is a symmetric if A is equal to A transpose. If we have a matrix A like this, it is equal to, for example, if we look at 3 by 3, and if it is A, B, C, this is also B, it is also C. D, E, this is E, and F. And if we interchange rows and columns, we will get exactly the same matrix. So this is a symmetric matrix. Two, three, four, 3, 4, 1, -1, -1, 5, for example. So this type of matrix is called a symmetric matrix. And what is special thing with this symmetric matrix and eigenvalues, which we just studied, that eigenvalues of a symmetric matrix are always real numbers. What eigenvalues of a symmetric matrix are always real. This is a property of symmetric matrices, that they have real eigenvalues. Okay. So symmetric matrix and the property of eigenvalue symmetric matrices, that they have only real eigenvalues. Now next is the definition of next result is that let A be a symmetric matrix, then the eigenvectors corresponding to distinct eigenvalues are orthogonal. You know, we have seen it before, even in 7.6. When do we say two vectors are orthogonal? When their dot product is 0. So as an example, let me say, if we have an eigenvector 2, 3, 4, and K2 is an eigenvector what should be K2 an eigenvector? Instead of because their dot product is 0, we can say like this: suppose -1, 2, and 1. And this is 1, 1, -1. Then what is K1 dot K2? 1 time -1 is -1, plus 2 time 1 is 2, plus 1 time -1 is -1, and this is equal to 0. So these two vectors are orthogonal vectors. And the result says that if we have a symmetric matrix, then the eigenvectors corresponding to distinct eigenvalues are orthogonal. Now, theorem 8.10.1 says that if a matrix is symmetric, then the eigenvalues are real. And next theorem says that if a symmetric matrix, then eigenvectors corresponding to distinct eigenvalues are orthogonal. Distinct.
Doctor?
Yes.
Shouldn't it be K1 transpose multiplied by K2 or dot K2?
You see,
The transpose of K1 dot K2.
yeah, when we you see, we cannot multiply matrices like this one. So this is simply saying what is the dot product of two vectors. But if they are actually vectors, any eigenvectors, for sure it will be transpose. Otherwise, we cannot multiply them. You are right. Otherwise, we cannot multiply them. But in that case, we should also remove the dot from between them. And here I was just telling what we learn when we learn vectors. We say that two vectors are orthogonal if their dot product is 0. So that was in my mind as a vectors, not as a matrices. Okay, you are right. We are not doing normal vectors. We are doing eigenvectors, which are actually matrices. Now, after learning these things,
Doctor,
yes, please.
how we can do transport for 3-1 vectors or 3-1 matrix?
What is a transpose of K1? This. You change rows to columns, columns to rows. Mazboot?
Okay.
So then the next thing here is now finally we reach to the definition of orthogonal matrix. Now here they are putting theorems in this dark blue color box and definitions in red color box. Anyway, and n by n non-singular. Here is to note that it is non-singular. Non-singular mean no eigenvalue is equal to 0. Lambda is non-zero. All eigenvalues, we say all lambda not equal to 0. So n by n non-singular matrix is orthogonal if its inverse is equal to A transpose. If A transpose is equal to A, it is symmetric. If A transpose is equal to A inverse, then it is defined as orthogonal matrix. Orthogonal matrix, any if A inverse is equal to A transpose, A inverse is equal to A transpose, then this implies multiply A inverse by A transpose by A, and this implies A transpose A is equal to identity. So if a matrix time is a transpose, and it is not only this, also A times A transpose, because it is equal to identity and transpose of identity is same. So we can also say that A time A transpose is identity, or matrix time its transpose is identity. So it is orthogonal matrix. This is what we conclude from this definition also. And then in your book, there is a solved example. There are several solved examples here. And a result theorem, which is based on this definition here, is that if we have an n by n non-singular matrix A, because whenever you say anything about this orthogonal matrix, it should be in your mind that it is a non-singular matrix. Because for a singular matrix, A inverse does not exist. Since orthogonal matrix is when we have A transpose equal to A inverse, and A inverse exists only if it is a non-singular. So it should be obvious that the matrix is non-singular about which we are talking about this idea of orthogonality. And the result, what it says, that if we have any orthogonal matrix, if we have a non-singular matrix A, and we say that A is orthogonal if and only if the eigenvectors, no, sorry, its columns, they form orthogonal set. The columns form orthogonal set. Okay. The columns form orthogonal set. Yani X I transpose times X J. You know a symbol notation delta Ij. Now this delta Ij is a notation in which the answer is 1 when I is equal to j, and answer is 0 when I and j are not equal. Maybe you have not seen this before, so see it now. Any x1 transpose x2 will be 0, x1 transpose x1 will be 1. And if you take transpose of a matrix, transpose of this column and multiply by itself, then it is 1. Otherwise, it is 0. In your book, they have given this same thing in a big notation like this. But in short, we can also write this way. So here you see they are taking A transpose A matrix as x1 transpose x1, x1 transpose x2, x1 transpose xn, and whenever they are same, yani when they are on the diagonal, it is 1 1 1, otherwise it is 0 0 0. So this is the say the theorem that if A is orthogonal, if an A is orthogonal if and only if columns. Now these are not eigenvectors. Usually here in our this book course, we denote eigenvectors by k. Usually we do not denote them by k. And here they are not k, they are columns of this matrix. So here we learn about this orthogonal matrices. Next thing is, okay teacher, what we have learned so far. What is a symmetric matrix? And if a matrix is symmetric, what happens with the eigenvalues and eigenvectors of a symmetric matrix? Eigenvalues of a symmetric matrix are real. Eigenvectors of a symmetric matrix corresponding to distinct eigenvalues are orthogonal. Then next thing is, what is the orthogonal matrix? Before we say about symmetric matrices, symmetric matrix, two result about symmetric matrix. Then orthogonal, definition of orthogonal matrix, and to check if matrix is orthogonal, multiply by its transpose and you get identity. This result, which is also clear from the definition that A transpose A time is equal to I, and that is explained here more in this theorem. Okay, what is the next thing? How to obtain an orthogonal matrix if we have eigenvectors given, if we have eigenvectors or given for a matrix, we can construct an orthogonal matrix okay. Um, Constructing orthogonal matrix. Next thing is, how can we construct an orthogonal matrix? Okay, let us do this. From here, we see that eigenvectors corresponding to distinct eigenvalues are orthogonal. So this thing help us to find, to construct an orthogonal matrix. Let us do this by example. we consider Shiva, during teaching, if you have some question, you better ask me, because while teaching, going to the chat part is not easy. Thank you, doctor. I'm leaving now. Who is this? Okay. Let us consider some example. And I will not completely do this example. Just give you the idea. 0, -1, 0. -1, -1, 1. 0, 1, 0. Okay. The eigenvalues of a symmetric matrix. Here, lambda 1 is 0. Lambda 2 is 1. Lambda 3 is -2. Now this matrix, can someone tell me, it is here on the screen, can someone tell me if this matrix itself, the matrix itself is a can be orthogonal or not? Without say actually checking A inverse equal to A transpose, just by looking so far, what information so far we have, can A be orthogonal or not?
It can be, but it's not. No, it's not It's singular.
You are saying it is not singular.
No, I mean it can be, but it's not non-singular. It's
No,
singular.
this matrix is a singular.
Yeah.
This matrix is singular. And you are seeing definition 8.10.2, what it says.
It's lambda it's not equal 0, then it's non-singular. But lambda down it's equal 0.
So this matrix
So it's
itself cannot be, this matrix by itself, it cannot be an orthogonal matrix. No way. Without checking, we can say, just looking by the eigenvalues, this eigenvalue is telling us this is a singular, but the definition of orthogonal matrix is for non-singular. So this matrix A cannot be an orthogonal matrix. Anyway, we are constructing an orthogonal matrix from a given symmetric matrix, but it is a symmetric. Not orthogonal, but it is symmetric. Now, what are three eigenvectors corresponding to these eigenvalues? It is a solved example. I'm not really solving it, but I'm just any solved mean eigenvalues and eigenvectors. I'm not say computing. I'm just using them. First is 1, 0, 1. Second is -1, 1, 1. Third is 1, 2, -1. Now, if we simply take their dot products, K1, K2, Let us check. Are they orthogonal? 1 time -1, 0 time 1, 1 time 1. Yes. K1 and K3. 1, 0, -1. Yes. K2, K3. -1, 2, -1. Yes. So their dot product is 0. So K1 transpose. Actually, in case of matrices, we need to do K1 transpose K2. It is 0. K1 transpose K3 is also 0 number. And K2 transpose K3, it is also 0 number. So these three vectors are orthogonal vectors. Should we put them in a matrix form? Because this theorem says that if we have a matrix in which columns are orthogonal, then it is orthogonal. Okay, my mistake here. In reading, I miss one information. They form orthonormal set. I wrote it, but I was just saying orthogonal, orthogonal, orthogonal. Actually, when this, I'm putting no check mark, when this condition is satisfied, we say one upper level of orthogonal, which is orthonormal. Orthonormal. Orthogonal is their dot product is 0. But orthonormal is that norm is equal to 1. Norm is equal to 1. Yani xi transpose multiply xi is equal to 1. Here norm is not equal to 1. So what do? We normalize these vectors. What do? We normalize these vectors. How do we normalize these vectors? What is the magnitude? If we consider them as vectors, then what is the magnitude of this 1, the first vector? What is its magnitude?
Square root of 2.
Square root of 2. You can say it like this. K1 norm, because no, we say norm, is equal to 1 square plus 0 square plus 1 square and then square root 2. So it is square root 2. Similarly, K2 norm is equal to square root of 3. Mazboot. And K3 norm is equal to 1 plus 4 plus 1 square root of 6. And we know that if we multiply a vector by a scalar, a number, then the scalar product of a vector, an eigenvector, is also an eigenvector corresponding to same eigenvalue. So what do? We divide each vector K1 since it is also an eigenvector, but we divide it by its magnitude. So what should we do? Let's say like this one. 1 over square root 2, 0, and 1 over square root 2. This is also an eigenvector corresponding to same eigenvalue. K2 tilde. I'm not saying bar because we use bar for complex. -1 over square root 3, 1 over square root 3, 1 over square root 3. And K3 tilde as 1 over square root of 6, 2 over square root of 6, minus 1 over square root of 6. And now when we put this in a matrix form, we put these eigenvectors in a matrix form with columns as these eigenvectors: 1 over square root 2, 0, 1 over square root 2, negative 1 over square root 3, positive 1 over square root 3, 1 over square root of 6, 2 over square root of 6, minus 1 over square root of 6. Now this is an orthogonal matrix. We can simplify this if we multiply by square root 6, or let us take square root of 6 in the denominator as a common factor. Sorry?
Yes, the second column shouldn't be positive 1 over square root of 3.
Minus, negative, positive, positive, minus, plus, plus.
Okay.
Yeah, so 1 over square root of 6, but still there will be square root inside with some entries.
Teacher,
Yes.
we use the norm after we multiply the K1 transport multiplied by K2, right?
No. That is just to check that they are orthogonal. That is, we verify that they are orthogonal.
So we should use the norm.
Now, first, when we say orthonormal, this result is saying that A is orthogonal if column vectors are orthonormal. Look, these two words underline. For A, we will say it is orthogonal when its column vectors are orthonormal. Orthonormal mean in this matrix P, the dot product of these column vectors, is a 0, and norm of each column vector is 1. Norm of each column vector or column is 1, and they are orthogonal. If we say orthogonal only, then their norm need not to be 1. Simply their product is 0. In case of vectors, we say their dot product is 0. In case of matrices, we say transpose of first column multiplied by second column, or transpose of first column multiply third column, transpose of a second column multiply third column, it is 0. And also norm of each column is equal to 1. Here, when I and j are equal, yani x I norm square, xi norm square is actually what? Xi transpose xi. When we take dot product of itself, it is magnitude square. And here for these columns, xi transpose multiply xi is actually norm square, and it should be equal to 1. Why? Because of this word orthonormal. Orthonormal mean orthogonal as well as norm of each column or vector is 1. norm of each column or vector. Each column considered as vector, norm is equal to 1. So for orthogonal, only one condition is satisfied, that their product is 0. But for orthonormal, two conditions. Number 1, they are orthogonal. Number 2, norm of each vector or column is equal to 1. So we construct matrix P from matrix A. We construct a matrix P from from a symmetric matrix A, and matrix P is orthogonal. This is how do we construct an orthogonal matrix from a given matrix. Now the given matrix should be this symmetric, because then we have for sure these eigenvalues are real and eigenvectors corresponding to distinct eigenvalues orthogonal. Eigenvectors are orthogonal, which corresponds to different eigenvalues.
Doctor,
Yes.
maybe we need to do some row operation to make it clear for the B matrix.
Row operations? Why? What do you mean by row operations?
I mean, if we multiply, or I mean divide the first row with 1 over root 3 and divide the second row with 1 over root 2, it will be, the diagonal will be the same.
Why we need that?
To make it clear, that's orthogonal.
No, you simply take the dot product of, you multiply first column by second column. What do you get? 1 over square root 2 multiply negative 1 over square root 3 is negative 1 over square root 6. 0 multiply 1 over square root 3 is 0. 1 over square root 2 multiply 1 over square root 3 is 1 over square root 6. When you add them together, what do you get? 0. So they are first column and second column are orthogonal. Similarly, you can check that first column and third column are orthogonal. You can also check that second column and third column are orthogonal. So all these three columns are orthogonal to each other, as well as norm of each column is equal to 1. So these columns are orthonormal. Columns are orthonormal, and matrix is orthogonal. Now, sometime we may have repeated eigenvalues, and I'm seeing here one example. Which is a symmetric matrix. This is example number 4 in your book. What is this matrix here? 7, 4, negative 4, 4, 4, negative 4, 8, negative 8, negative 1, negative 1, and negative 8. This is a matrix. We can see that it is symmetric. Now, A minus lambda I equal to A minus lambda I. Let us find its eigenvalues. Seven minus lambda, 4, -4. No, I need to have a big space. Then 4 here, -8 minus lambda, -1 here, -4, -1, -8 minus lambda. Okay. You can, let me save time. You can solve this and we'll get lambda 1 equal to lambda 2 is equal to -9 and lambda 3 is equal to +9. Here I'm not doing this just to save time to explain you more things. Okay. Lambda 1 and lambda 2 repeated, not distinct. So what happened when lambda 1, we take lambda 1 equal to -9 or lambda 2 equal to -9, what will happen? And if for these two eigenvalues, what will happen? What system we need to solve? 7 minus -9, 16. 4, -4, 0, 0, 0. Then 4 here, -8, -9 plus 9, -8 plus 9 is 1 here and -1. -4 here, -1 here and +1 here. Okay. Now from here we can make the first position as 1 by multiplying 1/16 row 1. 1/16 row 1. 1/4, -1/4, 0. 4, 1, 1, -1, 0. -4, -4, -1 and 1. Now -4 times row 1 add in row 2 and +4 times row 1 add in row 3. So 1/4, -1/4. -4, +4 is 0. When we multiply second column by 4, we get 1 here. -1 plus 1 is 0. And third column, multiply it by -4, negative, negative, +1, and then -1 is 0. This will always remain 0. Multiply by 4, add in the, multiply row 1 by 4. So 4 minus 4 is 0. Multiply by 4, 1 minus 1 is 0 and 0. Okay, so we have two row zeros, two free variables, small k1 plus 1/4 k2 minus 1/4 k3. This is 0, only one row. So let us do this. Write k1 is equal to -1/4 k2 plus 1/4 k3. So we have two free variables. We have two free variables. Let us choose k2 equal to 1 K2 equal to 4 and K3 is equal to 4. No, K3 equal to 0. Suppose we choose this one. K3 is 0, K2 is 4. When K2 is 4, K1 is a negative 1. K2 is a 4, K3 is 0. And this does not happen always for repeated eigenvalues. Shabab, listen. By chance here, we are able to find two linearly independent eigenvectors for the same eigenvalue. It is not necessary that we can always find two linearly independent eigenvectors for same eigenvalue. Maybe we can find only one eigenvector, which corresponds to two eigenvalues. Then to find the second eigenvector, which is linearly independent of this eigenvector, we have to use another procedure, which I have not told you so far. If we have that type of material in our syllabus, I will explain you. K2, you choose small k2 as 0 and small k3 as 4. And in that case, it is 1 and it is 0 and this is 4. Now, let me ask you, can you get K1 eigenvector from K2 eigenvector?
No.
So they are linearly independent. K1 and K2, big K2 are linearly independent. Question can be, find all linearly independent eigenvectors for this matrix. Find eigenvalues of A and linearly independent eigenvectors. So here by chance, luckily, without going to special procedure, we are able to find linearly independent eigenvectors. But our goal here is not to find linearly independent eigenvectors. Our goal here is to construct an orthogonal matrix using this given matrix. Now here, K1, K2, are they orthogonal? Hey, Shabab, should not take this much time. I'm asking.
No, Doctor.
They are not orthogonal. Mazboot? These are linearly independent, okay, but they are not orthogonal. All right. So,
Yes.
what should we do to get a second? What should we do to get two eigenvectors which are orthogonal? And for that, these K1 and K2 are not orthogonal. Okay. What do we do now? There is one.
With the norm.
Sorry. Say it again.
Bring the norm. Norm.
Norm.
Yes.
norm make their norm, if we multiply, if we divide K1 by its norm, then and K2 by its norm, then still they are not orthonormal because they are not orthogonal. So for norm, we go to the step of calculating norm. If they are orthogonal, then we divide each of them by its norm to make them orthonormal. Now, when they are not orthogonal, they cannot be orthonormal. Not a question. Okay, they are not orthogonal. And what process we are using, it is called Gram-Schmidt. SCHMIDT. D silent. Orthogonalization process. What is this? Let me write in black color. We can make two non-orthogonal matrices as orthogonal we can make two non-orthogonal vectors as orthogonal vectors. We let K1 as V1 and we define K2 as not K2. K2 is already with us. I should say, we say vector 1 is as one of these two, and vector 2 is second vector K2 minus K2 dot V1 over V1 dot V1. You can say here in this case also K2 transpose V1 over V1 by its transpose by itself, yani norm square, and multiply this whole thing a scalar number by V1. This is Gram-Schmidt process. You use this process and find a V2 vectors, and you will see that these V1 and V2, they are also eigenvectors. They are also eigenvectors. And a special thing is with these V1 and V2 that they will be orthogonal. They will be orthogonal. Then you will have V1, V2, and still we need to find K3, which is eigenvector corresponding to lambda 3 equal to 9. So then we will have these three eigenvectors which are orthogonal to each other. After that, we will normalize them and put them in the matrix form. I will continue from here. Now, let me take the attendance. Okay, and it is time for you to leave. And I will continue from this example tomorrow to explain this completely. But it is a solved example in your book. It is good for you if you complete this at home before I explain you tomorrow. And you can do this if you want. Any question?
Doctor?
Yes, Mukhtar.
The V1 and the V2 vectors are special for the area
No.
matrix, I mean.
V1, V2 is, we apply a special process to make non-orthogonal vectors, to transform non-orthogonal matrix into orthogonal non-orthogonal vectors into orthogonal vectors.
So there are not eigenvectors.
No. Listen.
Oh.
Listen. The set V1 and V2 is an orthogonal vectors. Moreover, the set V1, V2, V and K3 is an orthogonal set of eigenvectors. They will be eigenvectors. As I mentioned before, you can verify this. And tomorrow I will verify this. Look, now we have new vectors V1 and V2. V1 is the same as K1. So no question about K1 or V1 being eigenvector. Now the verify or question is only about V2. If we get V2 in this process, then is this V2 still an eigenvector? The answer is yes. And I will show you by multiplying this with the matrix. Yeah, see, this is still an eigenvector.
Okay, thank you.
Okay, but I suggest you, at least those who are really interested and they show their interest, I suggest you to do this at home before you come to class tomorrow. And if anything is not clear, ask me during the class. Okay.
Okay,
See you
thank you.
tomorrow, inshallah.
Thank you, Doctor.
You're welcome. If there is no question, let me